So, can you hear me? Okay. Okay. So, do you have, this is the assignment that's due this week. And it's basically doing advection in 2D. Okay. You've done advection in 1D already. This is doing it in 2D. So, do you have any questions about this?
For part F, question 1.
Part F in question 1, right?
My solution's blowing up, so I'm assuming it's unstable. I'm just not sure why. Stability analysis, I guess, is the next step to figuring that out.
Yeah, so, okay, you're saying for part F, your solution blows up.
Yeah.
Okay. What are the stability conditions we have considered?
CFL?
Yeah, for diffusion there's something, for CFL there's something else. So yeah, if you go flip through the order notes, you will find the CFL condition might be violated. That's why your solution blows up.
Well, I did my calculation and it wasn't being violated. So I figured there's...
How much was it?
0.8.
With second order upwind or first order?
Second order.
So the formulas we derived were valid for first order. When you go second order, yeah.
Okay.
Yeah. But yeah, that's the reason. As you keep decreasing your dx, the dt has to be dropped. So you will see that with 501 points, if you take smaller dt, you will get a solution again.
Okay.
Anything else? One hint that I do want to give you is, if you decide to use, so the boundary conditions given are periodic, right? And if you decide to use ghost cells for copying, just be careful of this. If we have a sine wave and x goes from 0 to 2 pi, right? And these are the grid nodes. Who is this node's right neighbor? So let's see. Which node is this node's right neighbor? So which one is it?
Node 2?
Yeah, it's not the first node.
Okay.
Because it's a periodic function, so this value is repeated over there, right? So if you want the right neighbor, you should look to the next one. Okay? And if you need two of those points, then you take these two. So you would copy these two over there. So that's just something to keep in mind. That you don't just take the first one to be the right neighbor for the last one. And the same on the other side. When you solve the equations, this might not show up as a big problem initially, but if you compute the divergence of the velocity, you will see at the boundary it will mess up unless you're careful with this. Okay. So let's see. Okay, so last time we were talking about vortex methods. Okay, and you know, we have the conservation laws. We have conservation of mass, conservation of momentum, and there's not a single way of solving it. You can use finite difference methods. You can use finite volume methods. You can use finite element methods even. And this is another class of methods called vortex methods. So most of the 2D simulations I have showed you use these vortex methods. So there's some advantages and potentially some disadvantages. So let's see. What we do is we take the vorticity equation. We take the vorticity form of the momentum equation. Okay, and for that we have to take the curl of the momentum equation. Okay, just as a reminder, this is curl and vorticity is defined as nabla cross u, curl of u. Okay, so when we take the curl of the full equation, we just get nabla cross b du by dt plus okay, and I think we had stopped there last time. Have we talked about this term, the barogenic term?
Baroclinic? Oh no. Yes.
Yeah, we had talked about this.
Expanded? You expanded?
Oh, okay, perfect. So yeah, the term here has a pressure and a rho density, and usually when we're dealing with normal simulations, density is constant everywhere. But sometimes density might not be constant. One blob might have a different density compared to another blob. It's still incompressible. In that case, this term actually expands out to minus 1 over rho squared nabla rho cross nabla p and a 0 and a new nabla squared omega. So when we take the curl of the diffusive term, we just get a diffusion of vorticity. Okay. When we take the curl of the pressure term, we get these two terms. Okay. The first term is non-zero only if rho is not constant in space. And the second expansion is actually 0. Why? Because this comes from nabla cross nabla p. Okay? And for any scalar, be it p, be it phi, be it temperature, this is a vector identity. That nabla cross nabla, let's say phi is equal to 0. And this is very easy to see. You can just expand out the cross product. So, did we do this last time?
No, but it's obvious, I think mathematically it's 0 because it's perpendicular to each other.
It's obvious that nabla cross nabla phi is...
For every property it's 0.
Okay, all right. Can you explain how? Because for me it wasn't, you know, I had to expand it out. So nabla phi is the gradient. Yeah, fine. Yes. And then you take the curl of the gradient. How do we think about this physically? Let's see. Yeah, I have to think more, but you know, for me it's never very obvious that this should always be equal to 0. So I expand it out. Phi jk, what goes here?
Partial over partial x. Partial over partial.
And then
UV job.
Or del phi by del x.
yeah. And again, phi is any scalar, the pressure, temperature. Okay, and then when we expand this out, we get, okay, the I term is d2 phi by dy dz minus d2 phi
Same.
by dz dy plus other terms. And this is 0, right? This is just interchanging the partial derivatives. So that's why this is 0. Okay? So this is a vector identity. All right, so now this, we'll go through all the terms one by one. This is a U, not an omega. All right, so the pressure term, the next part, okay, so the remaining pressure term is called the baroclinic term. Okay, and it actually plays a role in the shape of storms and hurricanes. Plays a role in the evolution the shape of hurricanes. Storms. Okay, and usually we have homogeneous fluid, which means nabla p, nabla rho is 0. Okay. All right. So in this case, the pressure term goes away completely. The pressure term disappears. In the vorticity equation. Is this a good thing or a bad thing? The pressure term goes away from the conservation of momentum. Should we be happy or should we be sad?
Happy.
You're saying happy, all right? Is it anybody sad? Why should you be happy?
Because I remember we were solving other equations I was adding another term to the momentum equation, I guess.
You mean the pressure projection?
Projection, yes. That was all about because of the pressure term.
Yeah, so there was this pressure projection we were solving before. And there was a Poisson's equation that we had to solve, which is very, very expensive, okay, computationally. So yes, you should be happy for the time being that the pressure term has gone away. Also, the boundary conditions for imposing pressure are always problematic. Okay? We looked at what to do near a wall, but there too we have to make an approximation. And when there's an open outflow boundary, people still argue what is the best pressure boundary condition to use there. Okay? So this is an advantage. since we don't have to deal with pressure boundary conditions. Also, we don't have to solve the pressure Poisson equation, the pressure Poisson equation, which is expensive. Okay? Does that seem to be too good to be true? Seems like I told you that 90% of the simulation time usually goes to solving the Poisson's equation. And we seem to have gotten rid of it. So, everybody should use vortex methods. So, it turns out that we actually will need to solve a different Poisson's equation. Okay? And we will get to that as we work through this. Okay, so the remaining terms, let's see, what are the remaining terms? So the remaining terms, let's see, we have a del omega by del t plus, this is a big term that is somewhat more problematic, and the right hand side is 0 plus u naught squared omega. Okay. So we have diffusion of vorticity. And we have the time change. This is not the full advection term. This is just time change. Rate of change of vorticity. Okay. And when we expand this term, we will get some additional terms. We will get, in the end, two extra terms. Okay. So let's do that. And for that, we will need to use more vector identities. So let's expand nap cross u dot nap u. Okay, and another vector identity is I have to look this up. Okay, so we need curl of the curl. Yeah, that should be close. Let's see. Yeah, this one. So let's see. Let me write that out. Half of nabla a dot a equal to a dot nabla a plus a cross nabla cross a. Okay, all right. Let's see. All right, so we have this, and we will use this vector identity over here. Let's see, what matches here? Okay, so this term inside looks the same as this term, the first term on the right hand side. Okay, so let's see, we have half of nabla of u dot u is equal to nabla cross. Did I make a mistake? Wait. So there's no mistake. All right, so this is u dot nabla u plus u cross nabla cross u squared. Okay, so yeah, okay, this looks good. So let's see. So this becomes u dot nabla u plus u cross omega.
So
Yeah, go ahead.
I think we should multiply nabla next step. Right?
Yeah, I'm just expanding the inside for now, right? So this term is exactly this here. So I can write, let's see, nabla cross u dot nabla u becomes nabla cross this guy plus dot minus u cross omega. Okay, I just took this on the other side and this replaces the thing inside here and you get nabla cross there. All right, and this u dot u is just u squared. Okay. Nabla cross nabla of u squared over 2 minus nabla cross or plus nabla cross omega cross u. Okay, I got rid of the minus sign by interchanging u and omega. Okay, what now?
First is 0.
First is 0. Why is first 0?
How was it? Because the properties,
Yeah, that's exactly what we were talking about here. Right? Gradient, curl of gradient of any scalar is 0. This is a scalar, this is kinetic energy. Gradient of the kinetic energy and the curl, which is 0. Okay, so now we have this term remaining. Okay, let's see. Okay.
So this term is plus or minus?
This?
Yes.
So there's a minus here.
Yes.
And it's
Okay.
u cross omega. I just split omega cross u, that's why this is a plus.
Okay.
Okay, and now we need another identity, which is, let me see. Nabla cross omega cross nabla cross omega cross u. It becomes nabla cross omega cross u. Okay, so all right, this is another vector identity. Let me expand it out. It's u dot nabla omega minus omega dot nabla u plus omega nabla dot u plus omega dot u lambda dot omega. Okay, so that's this term. This term expands out into 4. Do you see things that should be 0 here?
Divergence of U.
This is 0 because of incompressibility. And this is 0 because? Lambda dot lambda cross U.
Ah, yes.
Okay, this is also 0 because this is another vector identity. Okay. And again, you can expand it out and you will see that it will evaluate to 0. All right, so in the end, we have these final 2 terms remaining. Okay, and if we go back to our momentum equation, plug back into vorticity equation. So we have time derivative omega and these 2 terms plus u dot lambda omega minus omega dot lambda u equal nu lambda squared omega. Okay? Now, does this look more familiar? What are these 2 terms?
Advection looks similar to
This is the material derivative.
material derivative.
So this is, yeah, let's say advection term or material derivative. Just capital D omega over 2t. Let's take this minus to the other side, which is omega dot lambda u plus u lambda squared omega. Okay, so this is the full vorticity equation. There's no assumptions in here. The only assumption is incompressibility. And it's very clean and neat. Okay. Now, do you know what this term is called? I mean, maybe you have seen it before. It's called the vortex stretching term. And you've probably heard of turbulent law. So all source of turbulence is this guy. If you have a vortex tubes, it gets stretched out and deformed because of this term. Okay? If this term is 0, you will not get any turbulence. So, any questions up to this point? Okay, so let's see. This term is the source of generation of turbulence. In the flow. Okay, and there's something very strange that happens in 2D. In 2D, do you remember what vorticity behaves like in 2D? There's omega x and omega y or something else.
It was omega z and
Yeah, in 2D, omega is only one component. It's either out of plane or into the plane. So it's omega z. So omega vector actually becomes omega z in k. Okay? And it's a scalar. It's not really a vector. And if we compute this omega dot nabla u, intuitively, can you say what will happen?
Partial W partial Z times K times omega Z.
Let's expand it out again. So let's see. Let's expand omega dot nabla u. And if we just write it, okay, so this is 0I plus 0j plus omega z k dotted with del u by del x I plus del u by del y j plus
Partial W.
wait a minute. What am I doing? Okay. So this is a tensor, right? Yeah. Okay, so we have to write it as the matrix. So what does that mean? Do you know what I mean? No.
Partial U over partial X,
Yeah.
partial U over partial V, partial.
And the last one is 0, right? Because there's no z. We're talking about t. See? And then we have dv by dx, dv by dy, 0. And the last one?
0, 0, 0.
Yeah, again, we're looking at what happens in 2D. So there's no w term, and there's no z derivative. Okay? And then, what should I do? Omega dot w. Omega is a tensor, vector, right? And in 2D, we have 0, 0, and omega z. What does this become?
0.
It's 0. 0. You know, you can multiply it up, it will be 0. So, there is no vortex stretching in 2D. Can there be turbulence in 2D?
Sorry, what?
I told you that the source of turbulence in any fluid flow is the vortex stretching term. In 2D, this term is exactly 0. No assumptions on our part. So technically that means in 2D, there should be no turbulence. This makes sense?
No.
It does not. Right. Yeah, go ahead.
So, is it necessary that if the stretching term is 0, there will be no turbulence, because we have the advection term and there can be instabilities at very high velocities which can actually generate vorticity, but there won't be any cascading if the stretching term is 0. So, like, we can have turbulence in 2D, right?
Okay, so all right, you mentioned a lot of things that we have not talked about. We will probably not talk about. So, what happens in turbulent flow? For the last 2 classes, I will cover this more. Okay, how we simulate turbulent flow, how we do modeling. So, in turbulent flow, what happens is, first of all, okay, let's say you have a huge ship, an oil tanker, okay, and it generates a wave. The Reynolds number there is on the order of several million. But eventually the wave will die out, right? You know, you sit there for 10 minutes, 15 minutes, you'll still see some surf. But eventually, you know, it'll go back to being the normal ocean. Does this make sense? Why does it die out? You know, why doesn't it keep being disturbed all the time? Can you push the button? So, or if you're going to answer, go ahead.
Uh, yeah. So
Did you get the question?
you are asking the source of turbulence, right?
No, I'm asking if you have a wake behind a very large ship, it takes some time to, go back to normal until you don't see any surf anymore, until you don't see any wake, right? And do you know why that happens? First of all, why should the wake die out? What is causing it to die out?
The
And
viscosity is causing like the dissipation
yeah, so
by the viscosity.
yeah, it's the same idea as if you put your hand in a bucket of water and you disturb it. It will take maybe a few seconds to die out. For the huge ship that's maybe half a kilometer long, it can take minutes. Okay? And the reason for that is any disturbance you introduce into fluid is killed by viscous dissipation. The viscous diffusion that we're talking about is the term that destroys energy, okay? The kinetic energy that we introduce. And when you do this at very large Reynolds numbers, that energy has to be transferred from these very large scales. So when we're talking about a supertanker, it's causing disturbances on the order of several tens of meters. And this energy at these scales has to get transferred down to smaller and smaller scales. So very conceptually, people used to think about this as a cascade of vortices. Bigger vortices get broken down into smaller and smaller vortices. And eventually, when the vortices are small enough, the diffusion term is strong enough that it can kill it. Okay? That's the basic idea behind turbulence. Okay? So this vortex stretching term is what gives rise to that cascade of energy. Okay? So energy being transferred from bigger scales, the vortex stretching term destroys this bigger vortex and keeps creating smaller ones out. So there will be no physical mechanism to transfer this energy, but the flow will be not steady. There's this the nonlinear advection term, the u dot nabla u, that will still be present. So if you introduce a disturbance, it will just stay there. It will not get killed off. Again, it will because of the vortex term, of the diffusion term, but not because of this mechanism of cascading energy. Okay. So strictly speaking, in a physical sense, it's not turbulent, right? It will still be unsteady and disturbed flow, but there's no mechanism of energy transfer. Does that make sense?
Yeah, it
So,
does. But we can say that like uh, why can we say that the cascading, if it is present only, then the flow is turbulent? It can't be turbulent without cascading as well, right?
when you say turbulent, do you mean unsteady and chaotic seeming? Is that what you mean?
Yeah, like it's more than chaotic, but yeah.
So in the field, actually, the word turbulence is used very specifically. You have to have a minus 5/3 slope of the energy spectrum, and yeah. So if you're talking to a very a very established researcher in this field, they will always say, "Hey, is it fully developed turbulence?" And it's not the same as when we talk about, okay, there's turbulence in the airplane. Okay? Do you understand what I'm saying?
Yeah.
So the word turbulence is reserved for this very specific case, when you have this cascade of energy from larger scales to smaller scales. Okay? The flow
Okay.
will still be unsteady and it will be disturbed. Okay, so that was a.
Excuse me, I have a question, maybe not very relevant.
Go ahead.
For example, in 2D flow, you said we don't have the real turbulence.
Yeah.
And energy, there is no energy because there is no transfer of energy.
There's no inviscid transfer of energy. There is a viscous destruction of energy here.
So then how reduced order are applied to 2D flow, and then, for example, proper orthogonal decomposition based on different energy, mode energy. I don't know if that energy is the same as that energy of the flow. So then,
Okay.
you know,
Yeah.
I
So
don't get that.
now, so we are going into different class. That's fine. So when you talk about turbulence, at low Reynolds numbers, there is no turbulence. Things are laminar, they are very clean. You talk about flow over a cylinder. It's very laminar flow until you hit, let's say, Reynolds number 6,000, 7,000. Okay? It's unsteady, it's shedding, but it's laminar. Okay? It's
turbulent is after 200.
No.
Turbulent wake. The wake is turbulent.
The wake is unsteady after 200.
After 40, just 40.
After 40
is unsteady.
Okay. But when you say turbulent, what do you mean?
The wake is turbulent. Boundary layer is laminar. Boundary layer around the cylinder is laminar. I think the one you mentioned is the turbulent boundary layer around the cylinder.
So there's a difference between.
But the wake is after 200.
You're talking about. All right. Okay. So if you do experiments of flow over a cylinder, right, and you have inflow, you will get some vortex shedding. Correct?
Yes.
And for some length, it will not be turbulent, but beyond some length, it will be, because there's a local Reynolds number, REL or REX. Okay, so I think that's what you're talking about. If you go far enough in the way, things will become turbulent, yes, because the REX becomes very high. Close to the cylinder, you will still have laminar.
Well, that I think maybe it's confusing. REX is not defined for cylinder. For cylinder, it's just that the REX is for plate.
Yes. So there's an RED. That's the problem with the Reynolds number. You can define it with using any length scale, any velocity scale you want.
Yes.
Right? So there's an RED and an REX. Even if you talk about a flat plate, and this is a perfect example of flat plate, right? What does the boundary layer look like? Initially, it's
laminar and then transient and then goes to
and then it follows the turbulent profile. And it's the same idea. Why? Because we're talking about REX. Okay? And the same thing happens if you go far enough in the way. The REX or REL becomes sufficiently large that you can say, yes, we are fully turbulent. The reason I was telling you about this is at lower enough Reynolds numbers, this cascade of energy does not happen. Physically, the separation between the viscous dissipation and energy production is very small. Okay? So there's not enough space. Okay? I have to tell you about wave numbers and at low Reynolds numbers, there's not an opportunity for these larger scales to keep breaking down into smaller scales until viscous dissipation happens. At low Reynolds numbers, this viscous dissipation happens very close to where these large scales are being formed. Okay? So there's no need to establish this cascade of energy. That's why for low Reynolds numbers, we can use 2D simulations. But and maybe even 2D experiments. But if you keep increasing the Reynolds number, let's say beyond 3,000 or 4,000, you will see that now you'll get three-dimensional structures in experiments. If you have a cylinder and inflow, you will start getting three-dimensional structures behind the cylinder. Before 2,000, 3,000, everything will probably be planar. Does this make sense?
Yes.
You've done these experiments,
Yes.
right?
So what my question was, I mean, the energy term that is reduced order, for example, in 2D flow, how that relates to the 2D flow that is not inherently is not turbulent.
The energy term, how it relates to
Based on the equation we just mentioned,
here, yeah?
the second term is 0 for 2D flow,
Yeah, yes.
right? So and
In
then there is
reality,
in
is there ever 2D flow? In reality, there's usually no 2D flow, right? But if the inflow speed is small enough, everything remains planar because this term is very small. Okay.
I mean, even with that, even for example, assume it's possible, for example, in a simulation that is a 2D
Okay.
and flow, wave flow of cylinder.
All right.
That's a 2D flow,
Yeah.
and we assume it's there is no turbulence because we just proved it.
Yeah.
But proper or reduced orders are defined based on the energy mode of the wave, I guess. Energy modes, different energy modes.
Okay.
And my question is, what is that energy mode? What does basically there shouldn't be any energy related to the 2D flow.
No, why? I mean, if you have 2D flow, you still have kinetic energy in the flow, which you can decompose using whatever method you want. Principal component analysis, POD, DMD, whatever you want, right? So there's still energy in the flow. There's just, the only thing missing is this inviscid cascade of energy, which is a very specific thing, okay? And this inviscid cascade of energy is what people refer to as turbulence in fluid mechanics, okay?
Okay.
Not in general English, right? When we're sitting in an airplane, we say, there's turbulence when the plane shakes. So it's a very specific term in fluid mechanics used for that case, that scenario. Make sense?
Yes. The cascade of energy is different than the.
Yeah, so you still have an unsteady evolution of vortices which keep changing in time and in space. And yeah, you can analyze this in many different ways. The only thing that isn't there is this inviscid cascade. And yeah, they're still trying to look at this exact argument we're having in detail. It's still an ongoing topic. It has been an ongoing topic of research for decades, 30, 40 years. So 2D simulations are good for low Reynolds numbers, but if you start going beyond Reynolds number 3,000, 4,000, 5,000, you're done. You basically cannot, you're making an assumption that's not true physically. Okay. So where were we? Here. Let's see. What did I say? Okay. So in 2D, there's no mechanism for an inviscid cascade. So, cascade of energy contains, when we put it in quotes, turbulence cannot be simulated. In 2D. And again, remember, turbulence does not mean unsteady flow or disturbed flow. It's very specific to whether or not this inviscid cascade exists or not.
But for example, turbulence intensity can be defined, right?
Yeah, you can define, that's your u prime squared over 2. Yeah, of course. You can say my mean velocity subtracted from everything gives me u prime. It's just a fluctuation kind of energy. Okay. All right. Let me see where we go. Let me see if I need to tell you. Let's see. Okay. All right, so beyond RE equal, let's say 4,000 to 5,000, it's preferable to switch to pre simulations. Okay, and if you remember one thing, remember this. When you do 2D simulations, the Reynolds number is always limited. Okay? Anybody who shows you, oh look, this is a beautiful simulation of an airfoil at Reynolds number 20,000 or 2 million, immediately you should ask them, but this is 2D, well, what about turbulence? So keep that in mind. And for low Reynolds numbers, the experiments agree very well with, the simulations agree quite well with the experiments. For the reason that the implicit cascade almost doesn't exist. Okay, so let's see. All right, so we're still, well, we have been deriving the vorticity equation. Let's see, what should we do now? Okay, so let's see. Why did I write it? All right, so vorticity equation becomes d omega by dt. Actually, no vector. Nu Laplace squared omega. Okay, see, again, very clean, very compact. There would be a third term, the vortex stretching term, but we're only talking about 2D. All right, what should we do now?
Similar to Poisson equation for vorticity.
Similar to the Poisson. You're talking about the temperature heat equation.
Yes.
For temperature, right? Is that true? Does somebody not agree with that? This is the heat equation. Everybody agrees? This is the heat equation?
Just the kinematic that discusses this.
Yeah, fine. I mean, nu would be kappa, but who cares, right? But see, this is not partial in T. This is material derivative. So this is, if we expand it out, this is actually del omega by del T plus u dot lambda omega lambda squared omega. Right? So we have advection and we have diffusion. So this is like the advection diffusion equation. How should we solve this? Yes, come on. How should we solve this? Remember we were talking about the momentum equation. There were many, many terms in there. But we said, no, we don't want to look at all the terms simultaneously. What do?
Splitting.
We usually split these things, right? So we can split it. Into first advection, then diffusion, or first do diffusion, then advection. Okay, now if you start thinking about if you were to set this up on your computer, what would you do? Let's say I have this, let's say I have this rectangular domain and I give you a cylinder in the center, and you've seen simulations that were done with this configuration. What would you do? I say simulate this at Reynolds number 200. What would you do? Does this make sense, what I'm asking?
First we'll set up the grid.
Yeah, first you set up the grid, right? So first you discretize the whole thing. Always, whenever we go from a PDE to a numerical calculation, first we have to create the grid. And then what do we do next?
Boundary conditions.
Yeah, we need boundary conditions and initial conditions. Okay, let's assume I've given those to you. Now, what are you going to solve for at each of these grid nodes? So we have in the past solved for temperature, we have solved for phi.
Vorticity.
Yeah, so at each of these nodes, we will solve for omega. Okay. We will solve for omega at each of the grid points. Okay, so if we talk about a simpler problem, okay, so where let's say I have a domain and I give you that in a circular arrangement, there's a Gaussian distribution of vorticity. So I basically give you omega x comma y, and at t equals 0 is omega naught. Okay. Right? Does this make sense? So, I might say omega inside the circle is 10 units, for instance. And then what will you do? You will again create your grids, and then you will start solving this. You will take steps in time starting from n equals 0 to n equals 1, etc. And you can do this. You have done this, right? So let's see. Let's forget about the cylinder. Let's take the simpler example now. So let's say omega naught is a Gaussian distributed, is Gaussian distributed. Okay. So what with omega naught? Well, okay, let's stop there. It's Gaussian distributed. Okay. What do? So you need to solve d omega by dt plus u dot lambda omega equal nu lambda squared omega. Will you be able to compute this diffusion term? How will you be able to compute this diffusion term? Go ahead.
Just like we did for the momentum equation.
Yeah, so we have an ijn in the grid, right?
Yeah.
So we can write the second derivative as, this is just d2 omega over dx squared plus d2 omega over dy squared, right? And we can discretize it as omega at n, I plus 1, comma j, minus 2 omega I j n plus omega I minus 1 comma j n over delta x squared plus the delta y squared. Right? So fine, the right hand side is easy to discretize. Oh, sorry. Okay, and this we know we can write as
Omega ij n
omega
plus
I
1
j and n plus 1
minus omega ij n by delta t.
Okay, now remains this term. All right, so does anybody have any ideas on what we should do here?
We need to
Assume
get
U is positive or negative, upping your.
Okay, so you're talking about upwinding, what were you saying?
we need to get u ij.
Yeah, see, there's a problem here. On the grid, we have only put down omega values. There, U does not exist, right? There's no U anywhere at the moment. So that's a problem.
We can assume it or like from the initial condition?
Okay, if you assume it at time step 0, what will you do at the next time step? And see, there's a problem. You cannot assume it. All right, go ahead.
Why is omega taken as initial conditions? If we can take u as initial conditions, we get omega for the initial conditions from u, isn't it?
Yeah, that's
Because-
a good point. Yeah, you can start as U is given as the initial condition. Fine. What do you do for going from step 0 to step 1?
We know omega is dou u by dou y minus dou v by dou x, so we can use
Yeah,
it for, yeah.
that's correct. You can compute omega by taking the curl of U. And then, what do you do when you go from time step 0 to time step 1? So that's just staying at time step 0.
Yeah, so we expand this to the form of, this is u dou omega by dou x plus v dou omega by dou y.
This is u d omega by dx plus b d omega by dy. Correct?
Yeah.
And then we can take finite difference for d by dx,
Yeah.
d by dy.
Yeah.
That's good, but you're still at time step 0. When you go to time step n plus 1, what do you do?
No, that's the only unknown there in the equation.
Yeah, omega n plus 1 is the only unknown, but then u has to be at n plus 1, n, right?
So if it's a
Does this make sense?
steady state flow.
No. Wow, come on. Come on. You do cylinder experiments, there's no steady state. So what I'm saying is,
Assumption.
when you expand this, this is u I j at n and omega n, let's say I plus 1 comma j minus omega I minus 1 comma j at n over delta x, right? So I've just expanded the first term, correct? But u needs to be at n, right? U needs to be known, and for n equals 0, you're correct. I know this because this was the initial condition. What will happen when I go to the next step?
I mean, by when we go to the next step, we will be calculating omega n plus 1 for all the grid points, isn't it?
That's correct, yes. So we will have omega n plus 1 at all the grid points.
What about you?
Not you. So the question is clear now? There's a problem that we don't know what u is, because we are evolving omega in time. Yeah, go ahead. Oh, no. So if you remember, I was telling you about there's no free lunch, right? The Poisson's equation for pressure went away. But now we will actually need to recover u from omega by by solving another Poisson's equation. Okay? So, we will, let's see, we will evolve omega in time, but u remains unknown. And you mentioned that you can assume u, but you cannot, because omega and u are,
Correlated.
yeah, they are, omega is dependent on u. You cannot have them independent. Okay? So, we will need to extract that. Need to extract u from the omega. Okay. And this involves solving a Poisson's equation. So we're back to paying in terms of computational cost. So again, there's no free lunch. You had 90% of computation in the pressure Poisson equation. Now that will happen in the velocity Poisson equation. Okay? And to derive this, it's a very simple relation. Let's see. So we know omega is nav across u. So if we take the curl of this nav across u, and this is another vector identity which I have to look up here. Okay, let's see what the vector identity is. So it's right here. Curl of the curl. All right. Nav across A is nav A minus nav squared. Okay. So now you tell me, what should this become? What's the right hand side?
Yeah, conservation of mass gives us the second term, or the first term goes to 0. Continuity equation, I'm sorry. Yeah.
Okay. And
And the second term still exists. Yeah.
okay, so now we have our Poisson's equation. Nav squared u equal minus nav cross omega.
Excuse me, it was about omega, not u, right?
Once more.
Grace, the variable is omega is vorticity, but I didn't understand why you changed it to u.
This is by definition, right? Omega is nav cross u.
Yes?
And we're trying to figure out how we can derive u if we know omega. Okay? And solving this equation directly is not possible.
Yes, but from the vector identity, the next line, you replace a with omega, right?
No, it's u. This is u.
Oh, this is u.
Yeah, I'm sorry.
Oh, okay, sir. And
Make sense now?
and the next line is u to the after vector identity.
Yeah, so vector identity, this is
Next
used
slide.
to expand this, which becomes this. Okay? And see, before now, you should have been screaming at me, we're solving the momentum equation. What about conservation of mass? So that is enforced here. Okay. When we recover u from the omega field using this formula, we are enforcing the continuity V0, the divergence V0. So this is in a way equivalent to what pressure projection was doing. Okay. And now if we go back to our the vorticity equation, we have everything we need. We know how to figure out u if we are given omega, and omega is discretized as always using I, J, and N. Make sense? All right. So I think we should just describe. All right. So let's see. Here, what you did was you wanted me to expand the convection term, the advection term, using finite difference. But we could also do the whole thing using semi-Lagrangian, if you remember what it was. So usually, the split is solved using 1 d omega by dt equals 0 with a semi-Lagrangian advection. Where what we had was, you know, if you have grid points and you know the velocity of each of them, you can advect them forward and then distribute omega onto the grids. Right? So advect, then distribute. Using some form of interpolation from the x to the grid nodes. Okay? And then the second step is just d omega star over dt equal nu Laplace squared omega star. Where this omega star comes from, the solution of the advection. So let's advect that distribute to get omega star, which is an intermediate solution. Okay? And step 3 is recover u from omega using Laplace squared u equal minus lambda cross omega. And we've already talked about how to solve the Poisson's equation. You can form a big matrix, or you can use pseudo time stepping. Does everything make sense? This is a very nice, very elegant way of solving the Navier-Stokes equations. Okay, but again, every method has its own pros and cons, and the con here is, if you have a wall, what is the boundary condition for omega? So what do you think? At a wall, what is the boundary condition for velocity?
For velocity is 0.
Velocity is 0. U is 0, V is 0. And for omega, omega is also 0.
Not necessarily.
Actually, in a free flow, the only source of omega is wall. If you have uniform flow, there will be no vorticity in there unless there's a wall to generate vorticity. Okay. So vorticity at the wall is non-zero, and figuring out what this non-zero value is a problem. Okay, so I will show you that next time. And after that, we'll move on to finite volume methods. Okay. That's, again, another class of methods used to solve the Navier-Stokes equation. Any questions? Okay, So again, the homework is up and it's due this week. Please email me whenever you need to. It's conceptually it's easy, but implementing it is a bit of a hassle. So all right, then I will see you next week. Next class.
So you will document from there. You are not the contract paper in the contract. Right.
Yes, ready. I forgot. Can you turn off your computer because they will need to move it so they can renovate the room.
Okay, right now?
Whenever you have time, so they will probably do it tomorrow.
Okay, so before I leave to...
Yeah, whenever. We have to figure out where we can move it. Oh yes, Yoga.
Awesome.